Okay, ladies and gentlemen, welcome back to Meteorology for Professional Pilots. Let me just get a swig of water here. Okay, that's good. We could jump right in. Okay, we last left off on talking about condensation. We were talking about condensation in the last video and how as we drop our temperature and the air becomes down to its dew point and the air becomes saturated and the water vapor condenses, it condenses on the nearest available surface. So we had our confused picture of George Bush and what surfaces are in the atmosphere on which water vapor may condense. What's out there, because clearly we can see the glass. We can see water vapor condensing on the glass, but what is in the atmosphere? And the answer is something called condensation nuclei. Alright. The atmosphere is never completely clean. And there is an abundance of microscopic solid particles. Alright, so we talked about solid, liquid, and gas states, but they're solid particles in the atmosphere. They're very, very small, and they're called condensation nuclei. They're suspended in the air, just kind of floating around, and as you can see in this picture, you can see the dust particles just kind of hanging. Like if your grandmother asked you to go get something out of the attic for her, and there was a window in the attic, then you could see the beam of light coming in and shining on these particles that are just kind of hanging out. And as usual, I forgot to pull up my talking points here. Just give me a couple seconds. All right. So, condensation nuclei. They're solid particles. Alright, because things are in three states. They could be in a liquid, gas, or solid. These are solid particles floating in the air. Here's a better or closer picture of that light beam coming in. So these particles they're kind of like dust and salt, sodium chloride. I don't want to say the other chemical because I don't remember it correctly. So I don't want to put it out there on the video. But it's kind of like dust, salt, and combustion byproducts, like from factories, dust. Alright. And condensation nuclei, they have an affinity. Some condensation nuclei have an affinity for water, which means it draws water vapor to it. Some of them draw water vapor to themselves and induce condensation or sublimation. As water vapor condenses or sublimates on condensation nuclei, the particles begin to grow. They could be liquid particles like rain, drizzle, or they could be ice particles, ice pellets, ice crystals, hail. But what's happening is the water vapor is attaching itself to this floating particle that we can't see normally. Whether particles are ice or liquid or ice doesn't really depend on temperature, and liquid water may be present at temperatures well below freezing. That's called supercooled water. But what I wanted to do was I put a ruler here, and we got centimeters, and these tick marks would be the millimeters. Okay. So, and we can see how that compares to an inch, or half inch, or a quarter inch. So, the average raindrop size is 2 millimeters, so that'd be 2 of these tick marks. The average cloud droplet, this is a cloud droplet, doesn't fall. It just hangs in the air, thus giving you the cloud. But when you fly through the clouds, the plane gets wet. So this is a cloud droplet. It's 10% of 2 of these tick marks, so they're very small. And here is the average size. This is like a speck. So think of this on a scale being a big giant raindrop that's 2 millimeters. Then you got this, which is 10% as big, actually less than 10%. some, I guess that'd be 2%. Wow, okay. 2%. All right. And that's the cloud droplet. And this is the condensation nuclei. So this average cloud droplet attaches itself to the condensation nuclei. After this thing picks up, this is the condensation nuclei, the dark speck. And you can see it attracting water vapor. So as this thing picks up, it pulls and it grows like that, just to be a cloud. And it's got to get heavier and bigger to become a raindrop. So this is what the condensation nuclei starts out as. So I thought that was pretty interesting. We were going into super cool water because sometimes you could have a water droplet that does not freeze. And in that case, when we fly through it, this is what we get. We get in-flight icing. So freezing is complex, and liquid water droplets often condense or persist at colder temperatures than 0 degrees Celsius. So pure water freezes at 0 degrees Celsius, but you know what's mixed up in the atmosphere and all that really is not pure water. You know, you got combustion products, you got salt, you got dust particles. It's kind of a mixture. I'm not saying it's like unsafe for drinking, because a lot of people drink rainwater, but it's not pure H2O. That's what I'm saying, because stuff has been added to it. And that might have something to do with, it might have something to do with why you can get super cool droplets. It definitely has something to do with acid rain. But we can get super cool water droplets that don't freeze. They actually stay liquid, and then when they attach themselves, the wing will get wet, and then it will just frost up, and then it gets hit with a bunch of these super cool water droplets, and then you get in-flight icing. So we did talk about that. Water droplets are super cooled. When they strike an exposed object, the impact induces freezing. So we talked about that. You can look at that slide on your own. Super cool water drops are very often in abundance in a cloud at temperatures between 0 degrees Celsius and negative 15 degrees Celsius. So when you hit 0 degrees, that's really the freezing point. And if you're in any type of clouds, you need to be watching. If you don't have de-icing equipment, then you need to be, if it's a cloud and you don't get any icing and, you just scan, but you have to think about the possibility, the temperature's super cold. We may need to, think about landing somewhere if we start building up ice, or if we can see it on the wing strut, or you probably won't see it on the leading edge right away. But you'll definitely see it on the wing strut, and you'll definitely see it on this fuel tank vent. It'll be like crystallized or frosted. So usually at colder temperatures than negative 15 degrees, sublimation is prevalent. All right. So you might just get like ice crystals striking the aircraft, not necessarily freezing on impact. They probably just kind of be, they could attach, maybe, because there could be a variation in temperatures, but in really super cold environments, in my experience, I've not seen a lot of, it could be like negative 30 degrees, and, you can fly through a cloud. That cloud is mostly ice crystals, not a whole lot of suspended water droplets, and you could probably fly through there with no problem. And if you did have something, most of the airplanes that I fly now have de-icing equipment, so it's really not a factor at that point at high altitude and with the possible equipment. But in like a Cessna 172 like this, or this could be a Cessna 182, it does not have de-icing. The prop may be de-iced. I guess they could redo the plane or something like that, but typically in all the Cessnas that I've flown since I was 15 years old, I've never ever seen a Cessna 172 or 182 with a de-icing boot. Not saying it doesn't exist, I've just never seen it. So we're going to go and we're going to talk about moisture again. we have to go back to a clip or picture and a video when we talked about diurnal variation. This is the temperature, and basically at midnight we have a drop in temperature, right? Up until 6 in the morning. At 6 in the morning we get a sunrise, and the radiation the sun starts sending solar radiation to the earth, and it keeps doing it at 12 noon. It still keeps doing it a little bit after 12. You got some solar radiation coming in, and then as the sun starts to go down into the afternoon and set, the solar radiation decreases. The temperature then kind of in turn with the sunrise and the sunset. At 6 a.m. the sun rose, and it's going to set at 6 p.m. So we get an increase. This T is temperature. We get an increase in temperature. It goes up, 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 up. Goes to the maximum temperature for the day. It's around 3 o'clock, 3 o'clock. And then it starts dropping off. So this will be the nighttime. During clear nights with little or no wind, vegetation often cools by radiation to temperature at or below the dew point of the adjacent air. Alright, so this is a couple ways how we get moisture. This glass and this leaf have cooled to a temperature below the dew point of the air around it. Alright, so that's why the leaves get sweaty in the morning. That's why if I put ice water out in a warm room, the pitcher is going to sweat. Did I miss anything? Moisture collects on the leaves. Okay, warm room. I talked about that. Just that. Frost forms the same way as dew. The difference is the dew point of the surrounding air must be colder than freezing. So, in this situation, the outside air or air around the leaf, around the pitcher, is pretty much warmer than freezing. Frost occurs when it's colder than freezing. All right. So the water vapor sublimates directly to ice. So it goes, that water vapor in the air surrounding the leaf comes from water vapor, and then it goes directly to a solid. So it goes from gas to solid. And I don't think that's deposition. I don't know why the book called it sublimation, but I think that's deposition. And we're going to go back because gas, water vapor to solid, deposition. I was right. The book is saying it's sublimation. It sublimates the ice, but we're going to call it deposition. And where are we? I am going to go ahead and change that right now. So it doesn't sublet, it deposits. We're going to say deposits because it's deposition. Deposits. I'll do it right here with you guys. Okay, because we're all here to learn. I may make a mistake here and there, but I generally catch myself. And I'm not going to redo the whole video. I'm not perfect. I know a lot of things, and I want to teach you guys what I know. But I'm not going to sit here and be like, I've been flying for over 20 years and I know everything. No, no pilot knows everything. So, I'd like to think I'm a pretty decent instructor, and I'm just trying to give you guys what I know. So I changed it right there, live on YouTube. Alright, sometimes dew and form freezes. Sometimes dew forms and later freezes. And however, frozen dew is easily distinguished. Alright, so we know this is the thing. Sometimes water vapor deposits from water vapor right into a solid. Sometimes it goes from water vapor to liquid, condensation, and then it freezes. You can tell the difference because this is frost and this is not. We can see that this is a liquid state. So we know that it turned from gas to liquid and then it froze. Because it's clearer, you could see through it. It's very transparent. Where they use the word opaque. It's like frosty. Like if you haven't like defrosted your refrigerator in a while, that's the kind of ice you'll see. This, and that's a great analogy. Your freezer, yeah. You look in your freezer and you see how it gets all frosty with like the rough, sharp, jagged edge type of frost. And then we know that air went from the water vapor. When you open your refrigerator, close it, your freezer, you open, close it. Air keeps coming in, and the water vapor deposits on the wall of the freezer. And then that's how you get that ice. As opposed to ice in your ice tray is clear. See, I just came up with a new analogy to use. So I hope that made sense. We get frost, like when you get frost, because you open, close your refrigerator. The outside air gets trapped in, and the water vapor in that air actually deposits itself from water vapor to a solid, which is the frost in your old freezer. But when you put ice and water in an ice tray and then it freezes, it's very clear as opposed to the frost around the walls of your freezer. Yeah, I like that. Okay, this is going to bring us into cloud formation, and we need to talk about the cooling processes. There are three different basic processes that may cool air to saturation. All right, one, air moving over a colder surface. This colder surface brings down the temperature of the air. Stagnant air overlying the cooling surface. All right, so that same air could be just moved over a cooling surface by way of a front or a stationary front. We'll talk about fronts soon. Sorry, I burped there. And then expansional cooling and upward moving air. That has to do with lapse rate. We take a body of air and it has lifting action. It's warm, it has lifting action. It's lifted, heated from below, lifted. And then as it goes into the upper atmosphere, it cools down. Expansional cooling is the major cause of cloud formation. A cloud is a visible aggregate of minute water or ice particles suspended in air. So this cloud could be, probably not. It's probably water particles, or instead of ice particles. The upper altitudes are like cirrus clouds, like way, way, way up. Clouds way, way up. Those are composed of ice particles. If a cloud is on the ground, it's called fog. Man, those guys can barely see. When entire layers of cool air cool to saturation, fog or sheet-like clouds result. Saturation of localized updraft produces a towering cloud. A cloud may be composed of entirely liquid water, that was like one thing, or of ice crystals, or a mixture of both, depending on altitude and how it's positioned. Precipitation is an all-inclusive term, and it denotes drizzle, rain, snow, ice pellets, hail, crystals. Precipitation occurs when these particles grow in size and weight until the atmosphere can no longer hold them. So that goes back to our condensation nuclei, which had an affinity for water vapor attaching to it. And then it just more water vapor attaches to it, and it gets heavier and heavier and heavier. And then the particles, they can't stay up in the air anymore. They have to fall. The particles, they grow in two ways. One, I just mentioned, the water droplet or ice crystal forms. They continue to grow by additive condensation or sublimation. Water vapor playing a process in that. And condensation, temperature dropping or sublimation, directly onto the particle. Now this is a slower method, and so in this case you would get light drizzle or light rain or snow. And the faster way, where we get heavy rain or downpours, we have cloud particles. This is in your text. Cloud particles collide and merge into larger drops, and they detach and they grow like that. This process produces larger precipitation, bigger raindrops, and does so more rapidly than the simple condensation growth process that we mentioned before. Then we add upward currents that enhance the growth rate and support larger drops, as shown here on the left. So once we get an updraft and everything starts mixing together, the particles are just hanging out. Like, look, they're super light, they have dust on them, they ain't hurting nobody. But then we introduce some moist air, and the moist air particles or water vapor particles start attaching to the condensation nuclei, and then we get some updrafts, and that makes for some really, really, really nasty thunderstorms. The lifting action normally is caused by some heating from below. Terrestrial radiation, for you guys that have watched my other videos, and hopefully you're watching this in building block form. I encourage it, because you won't understand what's going on if you haven't looked at the previous videos. So precip is just short for precipitation formed by emerging drops with mild upward currents. Now you can have mild currents, that'll give you light to moderate rain of snow, but if you have strong upward currents here, then you're going to get some heavy rain, snow, and even possibly hail. Alright, so we got condensation happening in this case. We got sublimation, and they keep calling it sublimation when it goes with water vapor. I gotta research that a little bit, because the book keeps saying it, and there is something to it, but I see it as deposition because water vapor goes directly to a snowflake or ice crystal that's too heavy and falls. Ice pellets, hail, things of that nature. So I'm going to research that further. So for right now, we're saying sublimation forms when snowflakes and they reach the ground as snow. If the temperature remains below freezing, if the ground is cold, then we get snow on the ground. If it's warm, the snow didn't stick. All right. So precipitation can change its state as the temperature of its environment changes. As we showed you in that temperature inversion, we have a cold layer of air, a warm layer of air, and another cold layer of air. So you could be in that cold layer of air, it could be freezing rain or ice pellet, right? Or no, because this is a FAA question. You have freezing rain, right? It's cold, and then you have a warmer condition towards the surface, right? So at the upper air surface, it's freezing rain, right? And then it could come down to the lower atmosphere, and it could be, I don't know, freezing rain. It could turn into anything. It could be cooled. What would freezing rain turn to if it came through a warmer layer? If it came through a warmer layer, it might just be kind of like ice pellets or freezing rain. No, if it's freezing rain, it could be regular rain, depending on how cold the freezing rain was. If they're ice pellets, because you can have a warm air surface, temperature inversion, warm air, then a layer of cold air before it hits the ground. So it could get super cooled in that warm layer of air, colder layer of air, I'm sorry. And then freezing on impact, it could be freezing rain, or like it touches the aircraft wing in flight. Or it may freeze during its descent, falling as ice pellets. So you could have a temperature inversion, warmer air up top, all right, and I'm going to put some diagrams together for this because I don't want to confuse you guys, but I want you guys to listen to what I'm saying. Like, at a higher altitude, you have a cold layer of air. Think of it as a sandwich. In the middle of the sandwich is a warm layer of air, and at the bottom of the sandwich is a cold layer of air. So when it went from that first cold layer of air, cold, warm air, it could be anything. It could be snow. And then it goes to the warm layer of air, then it could turn into a cold raindrop. And then it can hit another layer of air, cooler, and it could turn into ice drops. My point is that the precipitation depending on how it's flying, it could go through different layers of air, and the air can affect that precipitation, changing it from rain to ice pellets to hail, or vice versa. So that's my point. I don't know why I got a brain fart on that one, but it's all right. So sometimes strong upward currents sustain large supercooled water droplets until some freeze subsequently. Other drops freeze to them, and then you could get hailstones. So all kinds of things could happen just by the precipitation going through different air masses and things of that nature. To produce a significant amount of precipitation, clouds have to be 4,000 feet thick or more. If you got 4,000 feet thickness in clouds, if from the bottom to the top you have 4,000 feet or more, you're going to get heavy precip. Alright. Shorter than that, you probably won't get too much precip. And when I say precipitation, I mean when I say precip, I mean precipitation. Alright. Land and water surfaces underlying the atmosphere greatly affect the clouds and precipitation development. This large body of water down here on the bottom is feeding water vapor into this weather system. That's just how it works. In this type of area where you have large bodies of water like this, like an ocean or a lake, you can expect low ceilings, meaning that the clouds are coming down real low to the ground, not necessarily fog at the fog level, but they could be like 1,000 feet above, 500 feet above the surface of the airport. If there's an airport nearby in this area, we get fog and we get precipitation, a lot of it, very frequently. Whenever you got the atmosphere and the winds over this wind trajectory over the water, it can pick up a lot of water vapor. Here's an example. This is Lake Michigan, and this is like a phenomenal photo of a fog layer. Almost looks like a wave crashing down, but no wave. That's all of a low-level cloud called fog. But this water has fed, Lake Michigan has fed this thing a lot of water vapor for the water vapor to condense. Here's another one. That's like crazy. You got the town here. You can see like the big hotel or resort here, whatever that is, but it's a big building. That's my point. You have smaller houses. This is the Great Lakes area, but wow, this is like a phenomenal picture. You could actually see it's like a sea of cloud, but it's low-level fog. Alright, so water vapor from the water feeds these things. And this is going to lead us to our wrap-up. Alright, lake effects. Here's a warm lake, here's a cold lake. We have winds or air mass. It's cold air, it's going to float over the warm lake. And this side is the leeward side. When they talk about the leeward side, this is the windward side, this is the leeward side. Where's the word leeward? It's around here. Yeah, leeward. Leeward side. This is the windward side, this is the leeward side. So we have cold air moving over a lake, and we get showers on the leeward side. We could have warm air flowing over a cold lake, and that warm air, what does it do? It condenses, and then we get fog. So, air moving over a sizable lake absorbs water vapor. Showers may appear on the leeward side if the air is colder than the water. When the air is warmer than the water, fog often develops on the leeward side. Alright, so I am going to leave it right there because we're coming up on 30 seconds. Not 30 seconds, 30 minutes. I hope this is all making sense. If it's really not clear, please send me a message. I really, really, really want to make this so simple that an eighth grader can understand it. And please like, share, and subscribe. I thank you guys for all your work. Just making an effort to watch the videos, and please share and subscribe. This is Kieno Thomas with Meteorology for Professional Pilots. I will talk to you again soon on the next video of this series. Thank you and bye-bye.